Hi class, welcome to your second lecture on finding the area between two curves. Now, in the previous lecture, what I did was I kind of introduced the theory behind it and worked just a couple examples. What I want to do in this section, in this lecture, I mean, is kind of also re-talk about the theory just real briefly, but then I want to do a bunch of examples. Two examples I'll do in detail, and then four other examples I'll talk about how you set them up. Because that's probably the hardest part in these lectures. Not necessarily doing the integration itself, but setting up the problems. All right. All right, so what we saw from the previous section is we want to have the formula for finding the area between two curves. Well, the area you're going to integrate from a to b, f1 of x minus f2 of x dx. Now, this will be the top curve minus the bottom curve. That's what we saw in the previous lecture. All right, so let me walk you through a little bit of theory on this one, again, just to kind of rehash. So how can we find the area between these two curves? So I've got y1, which looks like this. It's a parabola that opens downward, and I've got a linear equation or a line right here. All right, well, the process for this, you're going to consider a very thin vertical strip like this. And then the length of this strip is obviously the top curve minus the bottom curve, and it's ever changing, obviously, depending on what x is, the length is. All right, or another way you can do it is instead of writing it as y1 minus y2, you could do 2 minus x squared minus x. All right, since the width of the strip is a very small change in x, all right, we call that dx, or the differential of x. We talked about that before. So this is our length, and this is our width. So since the strip is a long, thin rectangle, the area of the strip is length times width, obviously. So this length is 2 minus x squared. It was minus x, so it became plus x. So that's our length. And then our width is dx. All right, so if we add up all these strips, obviously we just integrate. So it looked like from -1 to 2 along the x-axis. So you would just integrate this formula, integrate your area from -1 to 2. Right, so going through that, integrating each of these is pretty straightforward. Obviously, 2 integrates to 2x, x squared integrates to 1/3 x cubed, and x integrates to 1/2 x squared. And then you're just going to evaluate that using the fundamental theorem of calculus from -1 to 2. I won't bore you by talking about it in too much detail in the slides, but if you were to plug these values in, you'd get the following. A little bit of simplification gives you this. Even more, with common denominators, we can get this. And when we finalize, it becomes 27/6, or when we simplify this fraction, 9/2. So that would be the area between those two curves right there. So I think the integration part is not the hardest part. I think the hardest part is just setting up the integral, and then after you've set it up correctly, it kind of just follows in place. All right, let's try this one right here. All right, so find the area right above the x-axis that falls between y is equal to x minus 2 and the square root of x. All right, if we try to integrate with vertical strips, here's the thing. You have to integrate in two parts, right? You see where the bottom part of this strip ends here, whereas the bottom part of this strip is actually this line. So you could do that in two parts, and that's what it is just set up. And where this 2 comes from here is where the line y is equal to x minus 2 takes over. But you'd have to do two integrals, and maybe that's no problem. You could absolutely do that. All right, but we can find the same area instead using a horizontal strip. All right, this will allow you to do this problem in one integral. Why wouldn't you want to use one integral, which is nice? But what's the problem here is our width is dy, not dx anymore. All right, so since the width of the strip is dy, we find the lengths of the strip by solving for x, right, in terms of y. So we're going to take those two equations here, y is equal to square root of x and y is equal to x minus 2, and basically just solve for x. All right, so here, obviously, we'll just square both sides and get x is equal to y squared. On the other side, we'll just add 2 over and get y plus 2 is equal to x. All right, now since, as I was saying, the width is dy, and I've put it in terms, and I've solved each of the equations in terms of y. All right, this is how I'm going to set it up. I'm going to integrate. Where does this 0 and 2 come from? Well, that's the value of the y-axis. So from 0, and it looks like they intersect over here at 2. The top curve is this one, right? Because it's the one that's furthest out along the x-axis positively. So this one here is the top curve. So that instead of writing x minus 2, I'm going to write it as y plus 2. Minus the bottom curve is this square root curve, which instead of as square root of x, I'm going to write it as y squared. All right, so that's the length of the strip that I've been saying. That's the width right there. So you can simply integrate that very easily. Y integrates to 1/2 y squared, 2 integrates to 2y, and minus y squared integrates to 1/3 y cubed. And just using the fundamental theorem of calculus again, you're going to evaluate from 0 to 2. Plugging that in, if you plug 0 in, all of it goes away, so that's great. So when you plug the 2 into everything, it simplifies to this, which is just 10/3 right there. So it's up to you. You can totally do it as 2 integrals. I think it's probably about the same amount of work to change all the variables and solve it for x, and then do it with horizontal. But there's some problems that you'll go through, especially in your homework, where it'll be easier to do it with horizontal strips. All right, I've got 4 more examples here, and what I want to do is just set them up for you and then give you the final answer. On your own, what you can do is you can test the integrals and try to work them out yourselves and see if you get the same answers. All right, but let's find the area of the region between the graphs of the functions. So we got f of x is equal to x squared minus 4x plus 10, and the other function g of x is 4x minus x squared. What I'm saying here is I want you to find the area of the region between, for x, between 1 and 3 inclusive. All right, so that's what this part is here. All right, so the first thing you're gonna do is sketch the graph. All right, you want to find the boundaries / intersections. Well, that I give you right there, so that's perfectly done. So I'm going to put some vertical dotted lines here to help me know what I'm trying to find the area between. You can make a generic Riemann rectangle if you want to help you here. So the base and height are length times width. So obviously the width is dx. The length or the height is the top graph f minus the bottom graph g. So you're going to integrate the area of each generic rectangle here. So I'm going to integrate from 1 to 3 because that was the intersections. The top graph, or excuse me, the boundaries. The top graph, which is the blue one here, f, minus the bottom one, which is the red one here, g, dx. Now, if you integrate that correctly, and I'll let you do that on your own so you can verify that you know how to do that, that'll equal 16/3. Let's do another one. Find the area of the region enclosed by the parabolas y is equal to x squared and y is equal to 2x minus x squared. So again, when you sketch them right here, you'll see where what the graphs look like. So y is equal to x squared is the blue graph, so that's the bottom. And y is equal to 2x minus x squared, that's the red graph, that's the top. So you find the boundaries here. You can do that obviously just by looking at the graph. You're going to see that there's 0 and 1. But if you want to also know the boundaries, you can solve algebraically by setting the two equations equal to each other. So when you do this, right, you're obviously going to move the x squared over like this, or add, in this case, I subtracted these over and added that over. Factor, right, and you can see that the two solutions there are x is equal to 0 and 1, which are the same things we have over here. So you can do it by inspection with the graph. Sometimes that's not always easy though. So you can solve for the intersection points by setting the two equations equal to each other. All right, so that's going to give my bounds of integration right there. All right, so I'm going to put them there with the vertical dashed line. All right, so I'm going to, just like I did before, make the generic rectangle. My width here, my base is dx. My height, you're going to take the top graph and subtract the bottom graph. So when you correctly set up the integral here, all right, when we integrate the area of each rectangle, I get this. So I'm integrating from 0 to 1 of that area. And if you integrate that correctly, you'll just get 1/3. All right, let's do another one. This one's a little bit more complex. Find the area of the region bounded by the graphs y is equal to 8 over x squared, y is equal to 8x, and y is equal to x. All right, important to sketch it correctly. It looks like this. Right? I know it seems a little confusing. The green here is y is equal to x. The red is y is equal to 8x. And the blue is this graph here, 8 divided by x squared. All right, so this is tough because there's a bunch of ways you could do this. And unfortunately, it's going to, if you do a dx or dy integral here, it's going to be two integrals. So that's kind of tough. So you want to find the boundaries or where they intersect. So I'm going to set this one, 8x is equal to x. That's x is equal to 0. It intersects here. 8x is equal to 8 divided by x squared. That's gonna be x is equal to 1. So that's telling me they intersect here. All right, so that's 1. So that's telling me that my first integral I'm going to do is just from involving this graph and this graph. Finally, when I set the other one equal, x is equal to x squared, x is equal to 8 over x squared, excuse me, that you'll see is equal to 2. So that's this part here. So you see where I put 3 vertical lines here at all the intersection point? What that's telling me, because there's 3, is I'm going to need 2 integrals. I'm going to need an integral for over here. I'm going to need an integral for over here. All right, so they'll do the first generic one here. My base here is dx. My height is 8x is the red minus x, which is the green. On the other side, the width or base is still dx. The height here is the blue graph, which is 8 over x squared minus the bottom graph, which is x. So the first one, this integral, you have to be careful. I'm going to integrate from 0 to 1. And then this integral over here, I'm going to integrate from 1 to 2. So that's how you would set that up. Now, I'll let you integrate that on your own, but if you do it correctly, you should get 6. So verify that on your own after watching this video. Or you can pause the video and verify that. Let's do one last one. All right, let's do a trig one. We haven't done that yet, in this lecture at least. So let's find the area of the region bounded by the curves. Y is equal to sine of x, y is equal to cosine of x is equal to 0, and x is equal to pi over 2. All right, so when you sketch this graph here like this, and this, all right, you're going to see that we're going to need 2 different integrals here. All right, so when you figure out what the bounds are, you set them, the bounds here, it's telling you between x is equal to 0 and pi over 2. So these 2 for sure. But when you set sine of x is equal to cosine of x, that's going to happen at pi over 4. So when I put that in with a vertical line, it's telling me I'm going to have 2 integrals again. All right. The red is the cosine, so in the first integral, that'll be at the top. And the blue is the sine graph, so in the second integral, that'll be at the top. All right, so this first one here, my base is obviously dx, but my height of this rectangle here is going to be the cosine minus the sine. And then on the other side, it's just going to be the sine minus the cosine, like I said. All right, so this first integral is going to be from 0 to pi over 4. This second integral is going to be from pi over 4 to pi over 2. So when I set up the integrals, it should look like this. And again, I'll let you verify what the exact solution is, or when you do the solution on your own. But you should get 2 square roots of 2 minus 2 as the area of this and this when you combine them. All right, what other integral could be used here? Well, you could recognize that they're equal areas, so you could just do 2 times the first integral if you recognize that. That will also help you because they're symmetrical areas. Excuse me. All right, you could also do it this way. You just got to make sure that when you do that, you keep it positive if you're going to do just that one. All right, let's just talk about some general strategy for areas between curves when you do this. First thing you're going to do is you're going to sketch the curves, right, like I've been doing in all these examples. Second thing you want to do is decide if you want the vertical or horizontal strips. Obviously, pick whichever one is easier, right, to write formulas for the length of the strip, and or whichever one lets you integrate fewer times. That's what you're going to want to do. The third thing, you're going to write an expression for the area of the strips, right? If the width is dx, the length must be in terms of x. If the width is dy, the length must be in terms of y, obviously. Fourth one, find the limits of integration, right? If you're using dx, the limits are x values. If you're using dy, the limits are y values, obviously. So those are those bounds of integration. And then finally, the fifth thing, just integrate to find the area. Once you set up the integral, just go with it. Find the area.